you're saying this is an intermediate one? I'm not so sure this is an intermediate one. Why don't we discuss the other ones where I think you'll see that it's really not that difficult. So you're wrong if you think that the ellipse problem is actually way too difficult. That's actually more manageable than this. Did anyone solve this?
I did.
Were you able to figure this out? Yeah?
Yeah. I
Yeah,
saw.
you think it's easier than ellipse or harder than ellipse, or what is your sense?
It was just tedious. It wasn't really difficult.
Tedious, yeah, okay. Yeah, so let's not do this. Also, I would also go faster if I've spent some time looking at it, so there's no point in me sitting here and figuring out what it is that needs to be done. So let's talk about the sponge or the Menger problem. The sponge also has lots of details. Why don't we do the ellipse first? Okay, which to me is something that you really should know. It doesn't matter whether you remember any details or not. You should be able to figure this out, and you should know how to do this. So where is that? That's not it. Sorry, that was F, right? Yeah, this one. Okay, I'll give you a couple of minutes to read this, especially for some newcomers here. So do you want to explain the problem, summarize the problem for us?
I didn't even try that.
You didn't try
I
this?
saw
You
the
read
ellipse
this?
and I was like.
Okay, anyone else tried this? Do you want to summarize the problem for us?
I didn't.
You did?
Participate.
Oh, you didn't participate, oh, sorry, yeah. One of you?
We got stuck on E.
Yeah, we got stuck on you.
We did C, but
You
then got
didn't
stuck
look
on
at
E.
this?
And we didn't get to that
We're
one.
going in order?
What?
You
I
were
looked
doing
at it.
in order?
No.
So
We
you
didn't
tried
get
this, so
C.
why don't you explain to us?
Well, I didn't try. I looked at the problem.
Tell me the problem, doesn't matter.
I don't remember enough to summarize.
You don't even remember?
My understanding was that you were supposed to get the corners of like the edges of the ellipse, and then I was thinking that you would try to make like triangles to find. I think that you needed to find the vertices.
No,
of the
first
edges
explain the
of a
problem.
rectangle.
Forget about what you need to do.
Okay.
What is the problem?
You're making bounding boxes around ellipses.
Okay, and? What about these bounding boxes do you need? So every ellipse has a bounding box, right? And you want to know what? What do you want to output?
The XY coordinates of the tightest aligned bounding box.
Okay, explain that to me in English, don't read me, I can
Yeah.
read it too. Well, what are we asking?
Like the tightest fit bounding box around it.
I can explain it. So basically, like that ellipse that you're given is going to like occupy some points,
Yeah.
and you want to find out like the leftmost, the like rightmost, and the bottom and uppermost.
You want the equations of the vertical lines, you want the equations of the horizontal lines that bound it. Okay?
Yeah.
Now vertical lines, what is the equation of a vertical line? X equals something, right? So you want to know what is this x equals, what is the equation of this line, which means any point on this line has the x coordinate of whatever. Any point on this line has x equals something else. You want to know what those two lines are for the vertical bound, the sides of the bounding box. Every bounding box has two vertical sides and two horizontal sides. The vertical sides have equations x equals something. The horizontal sides have equations
Y equals something.
y equals something, right? So you want to know what those x and y's are, which is the same as saying, what is the bounding lines, what are the lines that bound the ellipse that's given to you? Is that clear? Wow, I see just blank faces. What's going on? Are you understanding this much? Yes? All right, good. Now, things are reasonably easy when the ellipse is well behaved. Now, what is a well behaved ellipse? Well, a well behaved ellipse looks something like this. because its axis is either horizontal or vertical, right? Those are nice ellipses. We can easily deal with them, and I'll go over how we do that. These guys that are a little rotated, they're really annoying. You have to work a little bit hard for those, and that's where much of our effort is going to be. Is that clear? Yeah? Okay, so now let's see a little bit more about the details. This says that every ellipse, the input for the ellipse is given in the strange form. It's given as 5 different integers, x1, y1, x2, y2, and a number. And this number is somewhere between 0 and 1,000. And you're told that the inputs actually tell you where the focus of the ellipse is, the foci of the ellipse are. Now, I'm sure you've taken this math class, and I'm sure you've seen this before, so it's just a matter of reminding you what this is. Now, every ellipse has 2 foci, so let's go here and work on this. Okay. So here's an ellipse, my ellipse. Let's assume it's kind of well behaved, which means that it will have a horizontal axis and a vertical axis. Okay. Now, if this horizontal axis and vertical axis are nice, if they are, sorry, I shouldn't say horizontal and vertical axis. I should say what's called as a major axis and a minor axis. So this is called the major axis, and this is called the minor axis. Major axis is the axis along which it's most elongated. That's it stretches the most. And the minor axis is the direction along which it's squished the most. Okay? And on the major axis, you have 2 points which are called the foci. So this is called focus 1, and this we'll call as focus 2. Doesn't really matter which one we call as 1 and 2. Now it turns out that the ellipse can be described as, anyone know this? In terms of the focus, what is it?
The sum of the distances of any point on the
That's
ellipse
right.
to both foci has to be
So if you
constant.
take, that's right, if you take any point on this ellipse, and if you take its distance to the 2 foci, and if you add these up, this number is always the same for any point on the ellipse. So, so you could go to that point there, and same thing over here. This distance plus this distance will be the same as for any other point on the ellipse. Same thing over here. This one, this distance plus this distance has to be the same. Okay, that's what we know what ellipse is. And this is a basic thing that you have to know, because otherwise you haven't really learned much from analytical geometry. That's the basic thing you learn in that class. Now, you guys have also learned about something called the circle. What's a circle?
All sides equal.
All the points are, well, here there's something called the center, right? And what we know is that any point on the circle is, what do we know?
Equal radius.
It's equidistant from that center, right? So this distance is the same as that distance, is the same as that distance. They're all at equal distance from the center. Here, what's the difference? Well, what has happened is that the center kind of breaks into 2 parts, becomes 2 foci, and instead of saying you're equidistant from the foci, you're saying the sum of the distance to the foci is kept constant. Okay? In fact, this gives you a way of drawing an ellipse. If you've ever seen these videos, they're quite nice, right? You can take a piece of string of a certain length and make a little nail on the wall here and a nail on the wall here, tie the string to those 2 points, and then if you stretch it as much as you can and if you pull that string, you'll get an ellipse. Okay. And that's because the string makes sure that the distance from the first focus to the second focus, to that point to the second focus, remains the same. So if you stretch this string, think of this red thing as a string. What happened here? So if you think of this this red piece as a string, as a red string, and you pull it as much as you can after you've tied it to the 2 nails, then it'll come up to here because the sum of this length is made that much. And if you just stretch it, if you just pull it around, you'll see that even though this distance may have increased, the sum of this plus this remains the same, right? And so what you get is an ellipse. So that's what you need to know about an ellipse. It's sort of a generalization of a circle. In a circle, you have only one center. Here, you have 2, you don't call them centers, you call them foci. All right? And instead of every point being equidistant from the center, here it is. You're saying it's the sum of the distances to the foci. Now, what is the equation of a circle?
X
Sorry?
squared.
So the equation of a circle is something like x squared plus y squared equals r squared, where r is
The radius.
the radius, right? So if this distance is r, then you get something like this, but this is a circle whose center is
0, comma 0.
is the origin.
The origin.
If you move the center somewhere else, if this is your origin at 0, 0, if you move your center somewhere else, it's going to look something like this. The equation of the circle is now going to be x squared plus y squared equals r squared. It's going to be something else. Now, we can talk about how that changes if this new center is given by h comma k. If the x coordinate is h and the y coordinate is k, then the equation of the circle turns out to be x minus h whole squared plus y minus k whole squared equals r squared. All right? So all that has happened is x gets replaced by x minus h, y gets replaced by y minus k. So you're moving the x coordinate system by h, you're moving the y coordinate system by k, and so x becomes x minus h, y becomes y minus k, the radius remains the same. So all it's saying is, that's the center, this gives you the distance for any point on the circle to h comma k, and that distance needs to be constant. Right? That's what you learned back in your geometry class in college, or maybe even in high school. Now, for the ellipse, it's a little bit strange. Now you have to find distance to 2 foci, and you have to write down an equation. Well, if you do all the necessary algebra, it turns out that the equation of an ellipse is something like this. It's all right. X squared divided by a squared plus y squared divided by b squared equals 1. All right. This again you must have seen back in your geometry class. This is a way to write down the equation of an ellipse. If a squared and b squared are the same, then what happens? I can take this denominator on the other side, and it becomes x squared plus y squared equals a squared, which is a circle. Okay, so if a and b are the same, really the ellipse becomes a circle. Fine? Now, if a and b are not the same, then you get an ellipse. Now, over here, it turns out that the let's see if we can make sense out of this. It turns out that this distance from here to here is 2a. So the width, the length of the major axis is 2 times a. All right? The length of the minor axis is 2 times b. All right? This is what's known. So if you know the major axis and minor axis lengths, then you can write down the equation of a standard ellipse where its center, by the way, this is called the center. Here we are assuming that the center is the origin. So if the center is the origin, and if the minor axis and major axis are a and b, and if a is bigger than b, then you will get an equation that looks like this. All right? So this is what we know. Now, if I take the ellipse and if I move it bodily, physically, then if I move it so that the center is not at the origin anymore, but it's, let's say, at h comma k, then the equation of the ellipse changes, and the equation changes exactly like we had before. In fact, we'll get x minus h whole squared divided by a squared plus y minus k whole squared divided by b squared equals 1. So all it did was x got replaced by x minus h, y got replaced by y minus k, and the ellipse just moves. Nothing else really changes. Fine? So we need to know this much before we kind of proceed. We still haven't talked about what happens when the ellipse gets rotated. Fine? Now all of this is useful because you're going to need that for your basic understanding of these ellipses. Now let's take a look at what is given to us. What we are told is that instead of giving us the length of the major axis and the minor axis, which would have been great, we're actually given the coordinates of the foci. All right? Now, that's a little bit different. So the foci are here. That's not really the major axis. So we have to do some work in order to figure out a and b and write down the equation. Fine? So here we are given as input x1, y1, and x2, y2 as the foci. By the way, you can, once you're given the foci, you can quickly figure out the center of the ellipse by doing what?
Midpoint.
You take the two foci and take the midpoint, and that's the center of the ellipse. And if the foci sit on a horizontal line, then your ellipse is a nice ellipse, because that's a standard ellipse. If it sits on a vertical line, if both the foci sit on a vertical line, that also is reasonably well behaved, except that x and y need to be switched. Okay? The other bizarre case is when it's rotated, in which case your x and y coordinates of the foci are not going to be the same. So if you look at this first example, your first focus is at minus 5, 0, and your second focus is at 5, 0. What does this tell you? That it's a nice horizontal one. Actually, there's a little bit more. Where is the center? It's at 0, 0 because that's at the midpoint of minus 5, 0 and plus 5, 0, right? Great, this is actually a good ellipse. We don't even need fancy stuff. We can figure this out more or less easily. Now, I still don't know, so I know that the equation is going to look something like this, right? But I don't know what A and B are.
You know A, you know A.
Well, you're given a fifth quantity, and that fifth quantity is the length of the major axis. Now, the length of the major axis is actually 2 times A, even though it says A there. That's the notation they use for the problem. So the length of the major axis is 2A. So great, we are actually given 2A, that's 16, so therefore A is 8. Great, so we're done with at least the first part of this. I am going to erase this part. All right. So now we've got A, according to this notation, A is 16 divided by 2, and that's 8. Fine? That's because really what we're given in the input is really the entire length of the major axis of the ellipse. So therefore A is 8. But we still have to figure out B in order to write down this equation. And the question is, how do I figure out B? For that, I now have been given the foci. I know that the two foci, this one is at minus 5 comma 0. This one is at 5 comma 0. Right? And I know that for the entire ellipse, the sum of the distances to the foci should be the same. Correct? And we know that, we know the coordinate of this point here. What is that? Because A is 8, this should be 8 comma 0. Right? Because A is 8, and this is the origin, so therefore that should be 8 comma 0. Right? And therefore this is what? Negative 8 comma 0. Great. Now it gives us some information that says the sum of the distance to the foci, we can actually figure this out. What is the sum of the distance to the two foci? Sum of distance to F1 and F2 equals what? So we know this point is on the ellipse. How far is it from F1? 3. So 3 plus the distance to the other foci is going to be 8 plus, sorry, this is 3, right? This distance is 3. This distance is 5. This distance is 5. So what is the sum of the distance to the two foci? One of them is 3, and the other is 13, right? So 3 plus 13 gives you 16. In fact, that's the same as the length of the major axis. Okay. And so with that help, we can figure out this guy here. Because now we know that the distance to the two foci from here is also going to be 16. Right? So what is that point? Well, we just have to kind of figure this out. This point here is going to have coordinates. What kind of coordinates is it going to have? It's going to have 0 comma b, and this one's going to have 0 comma
Negative b.
negative b, right? So 0 comma b to negative 5 comma 0. What's the distance? We know the distance formula, right? And the distance formula is going to be 0 minus 5 whole squared, so that's 5 squared, plus b minus 0 whole squared, so that's b squared. And this square root, that's the distance to first foci. And then the second one is going to be exactly the same, except it's going to be on this side. So we'll say it's 2 times this. We want this to be equal to 16, because that's what we are told. The distance to the foci, the sum of the distance to the foci must remain the same regardless of where you are. So if you're here, the distance to the 2 foci is 16. If you're here, the distance to the 2 foci, when you add them up, it's still 16. When you're here, it needs to remain as 16. So now we can figure out b. So therefore, what is b? Well, it's actually quite easy. We'll get square root of 5 squared plus b squared equals 16 divided by 2, that's 8. You do the math here, 5 squared plus b squared equals 64, and so b squared equals 49. So therefore b equals, did I get this right? No, I didn't get it right. What is it?
Should be 39.
39, 6 minus, yeah, it should be 39, yeah. Right, is that right? You guys understand?
Yeah, that's right.
Okay, so therefore b equals square root of 39. Which, by the way, if it's 36, it would be 6, so 39 is 6 point something, right? Are we good? Okay, so we figured out b now, and therefore we can write down the equation of this ellipse perfectly. What does that turn out to be? It's going to be x squared divided by a squared, which is 64, plus y squared divided by b squared, which is 39, equals 1. That's your equation of the ellipse. Is that clear? Now, we also know that the bounding box, actually we don't need to do any math here. The bounding box is now pretty easy to figure out, because the bounding box is going to be that vertical line and that vertical line, and this horizontal line and this horizontal line. And so therefore, we can figure out the coordinates of the ends of the bounding box. What are they asking? Are they asking for the endpoints of the bounding box?
Yeah.
The 2 endpoints?
Like the lowest x coordinate, highest x coordinate, lowest y coordinate, highest y coordinate.
Okay, okay. So lower left and upper right. Okay, good. So what they want is let's go to a different color here. What they want is where these two meet. So it's going to be right here. And this point here is going to have coordinates minus a minus b, right? Yeah. And that point there is going to have coordinates a comma. That's all you have to output here, and you can see here that your answers are -8, -6 point something, then +8 and +6 point something. Is that clear? So we can get the answer without doing any further math, but we still need to understand this a little bit more before we can go to the general case. Are we fine so far? Yeah? Okay, so there are other ways to figure out this vertical line and this horizontal line. And what would that be? Any thoughts on how else you would go about figuring this out? Straight from the equation of the ellipse? Yeah, I'm give them a couple minutes here. Any thoughts?
I was thinking maybe because it has to be parallel to like B.
Right.
So you would just like equals b and go up until a. Or
Yeah,
like-
but how do I find that? Is there, what's the, well, I don't know how to frame the question. All right, let me hear you.
You could use calculus.
You
'cause
can use
know-
calculus. You guys have taken calculus before, right? You know things like this maxima and minima. You remember this? How do you describe a maximum of a curve? Yes?
I forgot.
Yes? Yes? No? How do you determine the maximum of a curve? Of a function?
Determinant equal to 0.
Not determinant, you mean
Slope.
a derivative,
Derivative.
right? So remember, the derivative of the function gives you the slope of the tangent at that point, right? So you want the derivative to be equal to 0. Well, what is this derivative? That's something you did in calculus. How many of you have taken calculus? You all have, right? Good. Good. So we already know the equation of the curve. All we have to do is to set the derivative to 0 and see what happens, right? Now, let's see, I need some space here. Let me see if I can write it here. So we have the equation of the circle. The equation of the circle is x squared divided by 64 plus y squared divided by 39 equals 1. Now, let's try and do differentiation. So we differentiate with respect to x. When we differentiate with respect to x, what happens to this first term? X squared becomes? 2x. X squared becomes 2x, right? So you get 2x divided by 64 plus 2y times divided by 39 times, let me erase a little bit of this here. Plus 2y divided by 39 times dy by dx equals 0. Okay. And this gives us trying to scare us. Right, okay, fine. So what you end up seeing is the following. At the point where this curve has its maximum, right, which in this case is right here, yes, you see that dy by dx is 0 because that's when the derivative is 0. That's when the slope of the line that bounds it is 0, right? That's when you get the maximum. Anytime you get a maximum, you know that you have a horizontal line that acts as a tangent. Is that clear? Yes? That's what you should have learned in calculus, okay? Calculus says when you're having a peak, when you're having a maximum, the derivative there is 0, Fine? And the derivative is also the slope of the line that comes in. And that's the magical thing that you use here. So if this is set to 0, what do you get? You just get 2x over 64 equals 0, which means x is equal to 0. So this says the point at which the value of x at which the curve hits a maximum is when x equals 0. But when x equals 0, I plug it back into this equation, I get y squared equals 39, which means I get y equals plus or minus square root of 39. So this immediately gives us the 2 points where the maximum and the minimum occurs. They both have x equals 0, right? This is 0, this is 0, and the y value is square root of 39 and negative square root of 39. And that's how you get these two points. You can do the same thing for the vertical lines by differentiating with respect to y instead of differentiating with respect to x. So you will get that these the maximum and the minimum values of x happen when y is equal to 0. And then you can plug this back in and get the value of x. So that's how you compute the extreme points. All right? So essentially, if you have the equation, it's trivial to figure out the maximum or the minimum, because it's just a matter of doing differentiation. You'll have to write some code for differentiation, but actually that's easy. Because you know that ellipses have very nice equations. They're either going to look like this or like this, as long as the major axis is horizontal. Okay? So if you know the theory, this part becomes fairly reasonable. It's not incredibly challenging here. Okay? If you don't know this, then well, it's the same as anything else. If you've never seen this before, or if you've forgotten how this happens, then there's not much you can do. But you have access to books and you have access to material at your competitions, and all you have to do is to know the theory that says when you differentiate your curve, that's when you're going to find the maximum. This is what you need to know. This is what you need to sleep with tonight in your head, saying this is the theory. This is what calculus tells us. Calculus tells us that as long as you keep going up, the slope keeps increasing. But at the point where you've reached a peak, the slope is 0 because it's a horizontal line. Is that clear? So if you take the tangent here, it's still going up. If you take it over here, it's still going up. But when you get there, the slope is flat. It's not rising anymore. So the derivative is 0. That's the theory. Okay? This is all you have to remember, that the derivative is 0. Yes? So you plug that into the equation and you get the answers. Any questions about this? So, if I had this equation instead, meaning my center has moved, remember the equation changes if the center moves. If the center is at the origin, you get this. If the center changes, it's like this. Actually, I have some slides, so let me show you that instead. So you all know this circle, and you know that the equation of the circle is going to be x squared plus y squared equals something. Okay? If you move the circle, then it becomes x minus h whole squared plus y minus k whole squared equals something. And here, since it moved to -1, -2, this becomes x plus 1 whole squared plus y plus 2 whole squared. Is that clear? This is the ellipse equation. We said earlier that the equation of the ellipse is x squared divided by a squared plus y squared divided by b squared equals 1. Right? Let me put this in. All right, now if the ellipse is centered at the origin, the equation looks like this. If it is translated, if the center gets moved to h comma k, the equation changes to this. And if you expand this out, it will look like this. Because when you expand x minus h whole squared, what do you get? You get x squared term
H square.
minus 2hx plus h squared. Are you listening? Yes?
Yeah.
Okay. And so you will get an x squared term, you'll get a y squared term, you'll get an x term, you'll get a y term, and you'll get a constant term, whatever those numbers are. Okay? So you could have written the equation like this, or you could have written the equation like this. Clear? Now, if let's say this were your equation, then how do I figure out my maximum and minimum? Let's see how to figure this out, okay? Alright, so let's work with this second equation here, where, remind me again, when do you get this equation?
When it's been translated.
When it's been moved, when it's been translated, right? So if my equation looks like this, so if my equation looks like this, x minus h whole squared divided by a squared plus y minus k whole squared divided by b squared equals 1, then I can do the same thing that I did before and nothing really changes. Okay, so what I'll do is I will differentiate this, take the derivative, and equate the dy by dx equals 0. If I take the derivative here, what do I get? Anyone? 2 times x minus h divided by a squared plus 2 times y minus k divided by b squared times the derivative of y, dy by dx, right? And on the other side, it's 0 because constants term will go away. Now because y prime, the derivative is set to 0, right, at the top, so this term will simply disappear, right? Because derivative is 0. So therefore you get this equals 0, and when you do that, what do you get?
H.
You get 2 times x minus h divided by a squared equals 0, and then what is x?
H.
Do you understand why? I think we should just stop soon and go home because we're just too tired. Yes? Not clear?
The only way for that to be 0 is the numerator 0, so x has
because this is a constant, you take it on the other side, what happens? A squared times 0 will give you 0. A0 divided by 2 will give you 0. So therefore x minus h is equal to 0. Therefore x equals h. Right? So therefore, now it's telling us that for this curve, the maximum is going to happen at x equals h, which we know already because we took this whole ellipse and we moved it to h, right? So therefore, of course, it's not going to be a maximum at x equals 0. Instead, it's going to be at x equals h because it moved by h, right? So here, we moved right by h and we moved up by k. So therefore, it makes sense that x equals h is where the maximum is. Yes? And you'll do the similar math and you'll find that y equals k is where the other minimum, the maximum and minimum for x happens. And so therefore, all you have to do is to write down the equation in this form and read out h and k, and you'll have the answer for when the maximum and the minimum happens in the ellipse. Because it's still a regular ellipse except it's been moved. Right? Okay. By the way, you'll get the same thing if you were to use this form, and you can try this out. Let's see, where is that problem? So the problem is here. Right. No, they don't have an example with a different center. Sorry. Okay. So, yeah, maybe I'll leave that as it is. So the next thing to worry about is the more general form of ellipse, where you take the ellipse and you rotate it. Okay? We know how to deal with ellipses as long as it's centered at the origin or you moved it somewhere. Fine? So what happens when you rotate? It turns out that there's something fairly simple to do here. You can replace x by x cos phi minus y sine phi, where phi is the angle by which you rotate. And you replace y by y cos phi plus x sine phi. There's this magic that happens. As long as you know this, all you do is go and plug that in. Now what is phi here? Phi is the angle by which it rotates.
And how do we know that angle? Is that here?
That's something we'd have to figure out. And the reason we can figure it out in this problem is because, what are we given? We're given the foci. And if the foci are on the same horizontal line, there is no rotation, right? So therefore, the phi simply is the slope of the line that goes through the two foci. That's all. Right? Because remember, if right now my foci goes through the x-axis, if I'm rotating everything, the two foci are going to sit on a line whose slope is going to be something else, not 0. And therefore we can figure this out. So essentially, it's the slope of the line that contains the two foci, that's your phi. Or really, the slope is tan of that angle. So slope of a line, slope is tan of this phi. And what is tan? That's sine divided by cosine, right? So therefore, if you're given the two foci, you can figure out the phi, right? So all this theory you can forget. All you need to know is x gets replaced by something, y gets replaced by something else. And you plug that in. So now, now we have all the cases taken care of. This is the simplest form of the ellipse when the center is at the origin and the foci are along the x-axis. Here the center has moved to h comma k. Then you replace x by x minus h and y minus k. If you rotate it, then x becomes x cos phi minus y sin phi, and y becomes y cos phi plus x sin phi. So all I do is I replace this x by that, replace y by that, leave everything else the same. Now if I do both, if I rotate and move it, then I get the rotation term and I get the translation term. Get the rotation term and the translation term, and the equation still remains the same. Fine? And all it says is that the slope of the major axis is tan of this angle. Those are the things you need to know. So here, translation and rotation, those are what can happen. Now here is the interesting thing to see. If you only have translation, your equation looks like this, right? When you expand this out, here you'll get an x squared term, you'll get an x term and a constant term. Here you'll get a y squared term, a y term and a constant term. And you only get those terms. But if you have rotation, then you have x cos phi minus y sin phi. Well, let's forget about this. Let's look at this one here. X cos phi minus y sin phi whole squared. When you expand this out, what do you get? You get an x squared term, right? You get a y squared term, and you also get an xy term, because this gets multiplied by this, right? And so in a rotation, you will always see an xy term in the equation of the ellipse. In the translation, you will only see x and x squared, y and y squared terms, and nothing else. Good? So once you know this, then things become quite easy, because it doesn't matter what the equation is. All you do is go and take the derivative and set the one of the derivatives to 0. Fine? So all we're left with is, how do we arrive at the equation? In order to arrive at the equation, it's either going to be this, 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 or this. One of these four forms are enough. Because either you need to move it, you need to rotate it, or you need to rotate it and move it. These are the only things that are possible. And we have all those equations here. Fine? If we are going to move it, there is an h and k term that simply gets added or subtracted from x and y. If you're going to do some translations, rotations, then x, wherever you have x, you replace it by this guy here. Wherever you have y, you replace it by this guy here, and you're done. And then, once you have that, write it down, take the derivative, and then figure out what the terms are and solve for it. Great. So now we can solve the most general problem, and here's an example. Here is a rotated and translated ellipse. See that the center is somewhere here. It's not at the origin, right? And it's rotated. Now if you do some, you're told that the equation of the ellipse is given here. And what you need to see here is that it has an x squared term, a y squared term, an x term, a y term, but most importantly, it has the xy term. If this xy term were not there, then it's not rotated at all. Then it's just a translation, and you can figure it out. If you have that term, then for sure there is a rotation, and your job is to figure out how much the rotation is. Okay? If this is your equation, you can easily figure out what the bounds are. If you're given nicely in this form, then it's easy to figure out, and we can do that math right here. I am just going to erase everything. Is that okay?
Yeah.
All right. So if the equation of the ellipse is let's get right. If the equation of the ellipse is that 2x squared plus y squared. Now let me take everything on the other side and bring it over here, okay? And I get minus 2x minus 2y minus 2xy, and then plus 2 equals 0. This is what we have as the equation of this ellipse. We'll talk a little bit later about how we got that equation, but let's assume we know this. If we know this, it's really quite easy. You just do, what do you do? In order to find the bounding boxes, you just take a derivative, right? So 2x squared, when you take the derivative, becomes 4x plus, this would be 2y times dy by dx, and it'll go away, right?
Yeah.
So you'll get 2y times dy by dx, and this will go away, minus 2 minus 2 times dy by dx, sorry. So let's call it y prime, and this also will go away, right? This one is a little trickier because it's a product, and taking the derivative of a product is,
Summation.
you have to do the summation. You take x times the derivative of y plus y times the derivative of x, right? So if you're multiplying two things, f1 and f2, you get f1 times the derivative of f2 plus f2 times the derivative of f1. That's what you get. Okay. So over here, you're going to get what? Minus 2 times x times the derivative of y plus y times the derivative of x, which is just 1, right? And then the rest is just going to be equal to 0. Are you with me so far? So this term went away, this term went away, this term went away, and what do you get? You get 4x minus 2 minus 2y equals 0. Fine? In fact, this is the equation of either the major axis or the minor axis, depending on what you're looking at. Okay? So over here, you can't solve for x because you don't know x and y now. So you have to work a little bit harder. You have to plug this back into that equation. And so if you plug this back there, by the way, you can write this as 2x equals y plus 1. I'm just taking 2y and 2 on the other side, and I'm dividing by 2. So 2x equals y plus 1, and so I am, maybe I write this as y equals 2x minus 1. So I take this y equals 2x minus 1, plug that in here, plug that in here, plug that in here. I'll get a quadratic in x. I solve that for x, and those are my values of x. Okay? Or I can take the x values. I can replace x equals y plus 1 divided by 2. Plug that in there, and I'll get the value of y. So I know how to solve this. Okay, and you'll find that it will give you, in this case, it'll give you that point, because it's giving you the maximum and the minimum. All right. And in case you don't believe me, we can work this out. How much time do I have?
25 minutes.
I have only 5 minutes.
25.
Oh, 25. Okay. All right. Then let's just do it. So. So if I replace y equals 2x minus 1 over here, what do I get? I'm going to erase this. I'll get 2x squared plus y squared, which is 2x minus 1 whole squared, minus 2x minus 2 times 2x minus 1 minus 2x times 2x minus 1 plus 2 equals 0. Okay? So let's simplify this. By the way, there's 2 everywhere now, right? No, it's fine. Let's leave it there. So this gets you 2x squared. This gets you 4x squared plus 4x minus 1 minus 2x minus 4x plus 2 minus 4x plus 2x, sorry, 4x squared. Yeah. Plus 2x plus 2 equals 0. So this 4x squared and this 4x squared cancels out, right?
I think it's minus 4x.
4x and minus 4x will cancel out.
I think it's minus 4x.
Where?
4x squared, yeah. 4x
4x
squared.
squared plus 4x squared, no, this should, oh, this is
Yeah,
minus, you're right.
Yeah.
Oh, annoying. Okay. Alright, so this is going to be minus 4x,
Plus
then
1.
this should be plus 1, right?
Yeah.
Okay. Minus 2x minus 4x plus 2. This seems correct. That seems correct. Okay, so now I can't quite cancel it out.
Yeah.
And
Bring back that 4x. The 4x we canceled out.
oh, it does cancel out.
No, it
The
doesn't.
4x squared cancels out. The 4x does not.
Yeah, so there's a
But the
4x
2x and the 2x will cancel out, right?
Yeah, but I'm
Oh,
saying,
I can't quite cancel it. Are we good? So, let's write this down. We get 2x squared, and that's it. Then, we got minus 4x, that's minus 8x,
Plus 5.
plus 1 plus 5. So all we have to do is to solve this. Okay? And so solving this can be a bit of a pain, but there's a formula, fortunately, and the formula is x equals anyone? Negative b. In this case, negative b is 8, right? Plus or minus square root of
B squared minus.
b squared. That would be 64, right? B squared minus 4 times 2 times 5, right?
Yeah.
So that's 40. Divided by 280, which is 4. Fine? So this is something like 8 plus or minus square root of 24 divided by 4, which is 8 divided by 4, which is 2, plus or minus square root of 24 divided by 4. And I'm going to stick that 4 inside there, and you can divide that by well, I'll write this down as 24 divided by 16, which I can simplify as 3 times 8.
3
Sorry?
3 by 2.
3 by 2, yeah. So I'm going to just erase that and put 3 by 2. Is that clear? Good. So it's 2 plus or minus square root of 3 over 2. Square root of 3 is about 1.7. Sorry, square root of 3 over 2 is about 1.5, and square root of that is a little over 2, right? Because 1.4, no, I'm saying that wrong.
1.2.
Square root of 1.5 is how much?
It's about 1.2.
is about 1.2, yeah. So this is going to be 2 plus or minus about 1.2, give or take. So that should be about 3.2 or 0.8, right? That's what the value of x is. And you see here that x equals 3.8 is one of them, and x equals 0.8 is one of them. Well, actually it comes out to be a little bit less, so I don't know why. 2 minus 1.2 should be sorry?
It was a little greater than 1.2. It was like 1.22.
1.25-ish, because this is almost close to 5. So 5 divided by 4 should give you very close to 1.25. But still, it's, anyways, you see here that gives you the value of x at which these, no, sorry, this is the, I got that wrong. This is where the horizontal, the vertical peak is, that should give you this point, which is 3.2, right? And the other one is about 0.7, 0.8. Okay, so that's what the answers are, and it matches what we see in the picture. Is that clear? Now, if we do the same thing but with y, you would then find this point here, and this point here. Clear? And if we take this value of x and plug it back there, you can get the y. The details are really not so important. What you need to understand are the basic principles that says once we know the equation of the ellipse, take the derivative and stick it in and do the and then work out the math. Okay? In order to get the equation of the ellipse, that's a bit of hard work, and there you just use these principles here that says either it's centered at the origin, or it's centered somewhere else, or it's rotated and then translated. These are your only possibilities. It's got to be one of these. Either way, you need to know that in the translation term, if it's only translation, you'll only see x and y terms. If there is a rotation, you'll see an x1 term. Fine? These are the things you need to know. Yeah.
I just want to let you know, I was like playing around a little bit with that equation on Desmos. I don't think the translation for like the rotation was done correctly.
Yeah.
I think you have to, like, after you apply the rotation, then you have to, for every x term that appears after the rotation, you have to replace with like x minus h, and then.
So that's why the first thing to do is to move it to the center, and then work out the math. You could separate out those two pieces. You could decide to. You can't do the translation and then the rotation. You have to first rotate it and then translate it. So where is the math not working out? So it does depend on how you apply this tan of phi. You have to figure out whether it's positive slope or negative slope, and one of them will give you positive angle and the other will give you a negative angle. So it's possible that there could be something tricky over there.
Yeah.
But your point was
My
that
point is,
you do the translation last?
No, I'm saying do the translation first, but I'm saying that just subtracting h and k like isn't giving me the right translation vector. So you have to do like x minus k times cos phi minus y x minus h, x minus h times cos phi minus y minus k times sin phi squared over a squared plus.
Then you're doing translation and then rotation, and that's not correct. You have to do rotation first and then translate. So the translation term has to be separate like that. For sure. That just can't be right. The angle will be the same regardless of where you see it. In most cases, it's easy to figure out your center and figure out your HK and do the subtraction first, and then do the rest of the math. So in this example, right? So you can see here that this is the second example. Here, clearly, the foci are not on any horizontal line or vertical line, right? It's at some strange, bizarre angle. And the length of the major axis is 70. So let's see what this ellipse even looks like. I'm going to erase this, yeah? So here your first focus is at 51.23, and the second focus is at 1967. So let's call this F1, let's call this F2, it really doesn't matter. Where is the center? The midpoint of those two, right? So whatever is the midpoint of 51 and 19, that's going to be 35?
40.
No,
60.
1 plus 9, so it's 35, right?
Yeah,
So
35.
it's, yeah, 35, and then that one is going to be 45. Right? So that's your center. So I would take care of this separately, or you can leave it to the end and do the math. It really doesn't matter. But essentially, this is H and K get added to wherever your maximum and minimum are. So if you now assume that everything is centered at the origin, with the rest of the parameters being exactly what's given to you, whatever maximum and minimum you get, all you have to do is to move it right by 35 and move it up by 45. Or is it negative? No, that's correct. Yeah. Right. So essentially, it's like saying my center now is here, and by the way, is the ellipse like this or like this? So you can see here that, let's say this is 35 and 45, right? So the first guy is at 51.23, so it'll be somewhere here, and the second is somewhere there, right? So your ellipse is going to look something like that. Fine? Because your major axis sits like that. Okay? So therefore the angle is negative, something for you to keep in your mind as you work through this example. So now, how do I figure out this angle phi? Well, the slope of this line you can figure out from these two points. The slope of the line that goes through these 2 points, by the way, is if you remember the formula, the formula there is m equals y1 minus y2 divided by x1 minus x2, whatever that number is. Okay. In this case, y1 minus y2 will be 23 minus 67, and x1 minus x2 is 51 minus 19. This here is, what is it? 44 negative divided by 2, 9, 11, 32.
Yep.
Which is the same as negative
11 by
11 by 8. Okay. So what this tells you is that it's sloping down like this with a slope of negative 11 by 8, and that's your tan theta, the tan of phi, right? So this is tan of phi. So therefore phi is tan inverse of this value. with this, you can pretty much figure out the equation. Well, it doesn't give you cos phi and sin phi. How do you figure that out? So again, you have to work a little bit harder. Tan phi is sin phi divided by cos phi. But you also know, so let's say this is x and this is y. We have to figure those out. But we also know a second equation which says sin squared phi plus cos squared phi is what?
1.
Right? So all we have to do is to use these two equations and figure out sin phi and cos phi. Once you figure that out, plug it into your equation, you'll get the equation that you want, and then you simply take the derivative and solve the problem. Drop something. Is all of this clear? So there's a lot of little subroutines to take care of. In the real competition, what you would do is you would have a lot of this, lot of the basic tools worked out earlier before you go to the competition, and you would have code for rotating if any object. It doesn't matter whether it's an ellipse or something else. And you will have code for translation. You will have code for derivatives. You will have code for solving a quadratic equation. You will have code for trying to figure out things like this. So all you have to do is to kind of just use those pieces of code. And once we know all of these pieces, it's not that challenging to write this. Does that make sense? Now we don't have any more time, I think. Yeah. We should probably stop here, but